In this next example, we're given a vector field B, which is equal to rho cosine phi in our rho direction plus sine of phi in our phi direction. And we want to evaluate the circulation of B around some path. And so the path is ABCDA as shown in this figure below. So as you can see here, we're looking at the XY plane, and I've drawn sort of lines, dashed lines for two angles, 30 degrees and 60 degrees. So those are different phi angles, as well as two different sort of what I've tried to do as sort of arcs. So an arc with rho equals 5 and an arc with rho equals 2. And so I've got our path here with arrows indicated by the blue line. And so what we can do is, as we've seen in a previous example when we were talking about line integrals, we can divide this integral into segments, and we can say that the integral around this closed path of b dot dl, which is the circulation of B around this path, is equal to, and then we could have the integral from A to B plus the integral from B to C plus the integral from C to D plus the integral from D to A, all of those evaluated for B dot dl. And so if you want to see details on how to do that method, you can look on page 88, and so that will go through step by step. But what we can do to make our lives a little bit easier here is we can use our Stokes theorem. So let's come down to here, and we can say alternatively, use Stokes theorem. And so remember what Stokes theorem says is that if we have this, so if we want to find this circulation around some path L of B dot dl, that's equal to the surface integral of the curl of B dot rds. So we need to figure out a couple things then. We need to figure out what is the curl of our vector field B, and we need to figure out our ds vector. So let's start with the curl of B. So curl of B is what we're looking for. So we notice that our vector field B is given in cylindrical coordinates. So we have a rho component and a phi component. So we have no z component in this case. So we want to go back to our equations from the previous videos where we had an equation for our curl in cylindrical coordinates. So doing that, we have that this is 1 over rho times the partial with respect to phi of our z component, but in this case we have 0 z component, so that's 0, minus the partial with respect to z of our phi component, which is sine of phi, and so all of that is in our rho direction. We then have plus the partial with respect to z of our rho component, which is rho cosine phi, minus the partial with respect to rho of our z component, which again is 0, and all of that is multiplied by our phi unit vector. And so finally we have plus 1 over rho times the partial with respect to rho of rho times our phi component, so we have rho sine phi, minus the partial with respect to phi of our rho cosine phi, so our phi component, and that is in our z direction. Okay, and so we can see, of course, we have two terms going to 0 because we have a 0 z component, so we can evaluate our other terms as well. So here we have del cross b is equal to, so that first term was 0. Now the partial with respect to z of sine of phi is also going to be 0, so we see we're going to have 0 rho component, plus now partial with respect to z of rho cosine phi is also going to be 0, and then our second term we already determined was 0, so we have 0 phi component as well. And then finally we're going to have 1 over rho times the partial with respect to rho of rho sine of phi, and so that's going to leave us with just sine of phi, and then we have minus the partial with respect to rho of rho cosine phi. And so that's going to be a negative sign. So we'll get negative minus a negative sign is going to be plus rho sine of phi. So the rho is just like a constant when we're deriving with respect to phi. And so all of that is in our z direction. So our curl of b simplifies then to sine of phi over rho plus sine of phi in our z direction. So just multiplying through that 1 over rho that was out front. Okay, so that's our curl of b. The other thing we needed was this ds. So how do we determine that ds? Remember, we use our right hand rule. So coming back to our figure here, we're going to put our fingers in the direction of the arrows such that our fingers on our right hand can curl inwards towards the surface. So if I put my fingers in this direction, they should be curling inward here. And so our right thumb is then pointing in the direction of ds, so it's coming out of the page. So based on the fact that we have x here and y here, our z, our positive z-axis is out of the page. So we're going to have then for our ds, so that's going to be equal to that differential surface area, which is d phi d rho, and it's going to be in our z direction. So now we're just putting this information together into this equation here, so we can utilize Stokes Theorem. So we know that the circulation of B around L, which is what we're ultimately looking for, is equal to the surface integral of, and so now we have the curl of our vector B, which is sine of phi plus rho sine of phi in our, so I've kind of sort of skipped a step here in my notes, but basically we're taking the dot product of these two things here. So dot product of this and this, they both only have z direction components, so it's essentially just going to be this times this. So these two highlighted things multiplied by one another. So we have sine of phi plus rho sine of phi times d phi d rho. So I've just multiplied through this rho right here is why I have sine of phi plus rho sine of phi. Okay, well, of course I can factor out that sine of phi so that we can separate, so not equals to, I can factor out that sine of phi so we can separate our variables. So I can say this is equal to the integral over the surface of sine of phi times the quantity of 1 plus rho d phi d rho. And so now I can separate and integrate, so I can say this is the integral from phi equals 30 degrees to 60 degrees of sine of phi d phi times the integral from rho equals 2 to 5 of 1 plus rho d rho. Okay, so now it's just a matter of evaluating these two integrals. So for this first one, we have negative cosine of phi evaluated between 30 degrees and 60 degrees multiplied by rho plus rho squared over 2 evaluated between 2 and 5. And so plugging that in, what we get is approximately 4.941. And so this would be our circulation of B around L. And so again, keep in mind, we could have done that by doing line integrals of each of the individual segments, but using Stokes' theorem, we can do that a little bit quicker.